Alright, hi everyone. Thanks for coming. I'm Chloe. I'm going to be presenting on regularization today. For those of you who haven't signed in, is anyone not signed in, or can I continue? Alright, everyone signed in. Cool. So, I'm going to be presenting on regularization. So before I start, I do want to do a brief review of the concepts that we've encountered before. I know one guy here hasn't come to any other workshop, so you'll be a little lost, but you'll be all right. Okay, so recall from last week we learned about neural networks, which are essentially layers of nodes capable of modeling very high dimensional data. So how does it do this? You have a data set of anywhere from tens of thousands to millions of examples, which you propagate forward through your network. You compute the cost, the error, and then you back propagate through your network and update your weights accordingly. And by the end of training, you hope to end up with a model that has, quote unquote, learned this data, that can map an input to the correct output. Okay. So before I get into what regularization actually is, we need to go over a couple of new concepts. So I'm going to talk about generalization, data and complexity, bias and variance, and then we're going to go into a couple of specific regularization techniques like weight decay, early stopping, dropout layer, and dataset augmentation. So feel free to stop me at any point with questions. Okay, so we're going to start with generalization. Generalization we like to call the goal of machine learning. So a definition that I like of generalization is the ability of an algorithm to perform well on data that it was not trained on. So what we want to remember when we're training our algorithms, and something that's going to come up a lot throughout the rest of this workshop, is that performance on your training data does not necessarily indicate good performance in real world or on your testing data. So what is generalization really? So when you train a neural network, you want it to capture the more general underlying patterns of your data. You don't want it to memorize the specifics of the individual examples that you're giving it, because then it will just memorize and it won't be able to generalize to further examples that it hasn't previously seen. Okay, so I'm going to start by talking a little bit about data. So the process of training an algorithm we can split up loosely into three stages. Our training stage, our validation stage, and our test/holdout stage. Some of these go by different names. Validation is also called dev set, but this is basically what they are. So what they're for is, machine learning is a very iterative process. There are a lot of hyperparameters that you need to tune, and you can't always guess the first time what the correct values are. So typically what you do is you come up with several models, you train them all on your training set, then you compare them on your validation set, then you pick the best one, and that one you prove out on your test or your holdout set to see what the actual performance is. So the split, when I talk about data split, I talk about how are you going to partition up your data set and what percentage is going to go to each stage. So it used to be considered best practice to divide up your data like this, broadly 70-30 or 60-20-20. But nowadays we have so much data available to us that if you have 1 million examples that you're going through, you don't need 200,000 examples for testing. So my point is, split depends on how much data you have available to you. There's no longer this golden ratio. And dataset balance is the idea that you should evenly represent each class that you're trying to classify in a model. I'll explain a little bit more about that in a second. So first I want to talk about dataset bias in two examples. So say you are creating a model that is trying to classify dogs, cats, and fish. And if 90% of your dataset is fish pictures, and 10% are dogs and cats, your model will perform very well when it comes to classifying fish and very poorly when it comes to differentiating between cats and dogs. Now, a real-life example. In 2015, Google Pictures identified a black woman as a gorilla, causing public outrage, of course. And knowing what you know now, why do you think it happened. It's because often in these huge data sets that even companies like Google use, there isn't a balance of data, and not everyone is equally represented, and it leads to problems like this. So it's important to remember when you're picking data and when you're training your algorithms that they can have this kind of real-world impact. Another example, police across the world and even in the US have started to use facial recognition technology to find and identify criminals. So the consequences of misidentifying a face can be much more severe in that case. Okay, so now I'm going to talk specifically about bias and its opposite, which is variance. So bias describes how far are your results from the true values, basically how inaccurate are your predictions. And this can indicate a lack of complexity in your model. So for example, say you're trying to fit a very high order polynomial with a single line. It's not going to work. Your line is not complex enough to accurately model your high order polynomial, and you need to increase the complexity. So variance is the opposite problem. Variance says how dissimilar are your results from each other. So how inconsistent are your predictions? So this could be basically the spread of your results across a given area, and it can indicate excessive complexity in your model. So I want to emphasize right now that bias and variance are opposite problems with opposite solutions. To fix bias, you need to increase complexity. To fix variance, you need to decrease complexity in your model. So a visual example, if you want, what we're going for is low bias and low variance. So that means low error and a tight group, lots of consistency. So if you take a look at the targets, obviously the little blue dots are your predictions, your results. And what we're going for is the center, the red center of the target. That's our expected output, or like our true value that we're trying to hit. So what high variance and low bias would look like on the top right. Since we have low bias, we have low error. On average, our results are correct, but they're inconsistent. An individual result, individually, your results are inconsistent and they're not necessarily correct. So the opposite problem is low variance and high bias. So low variance means your results are consistent, but high bias means they're wrong, so they're consistently incorrect, and that's not what we want either. Worst case scenario, high variance, high bias, your results are inconsistent and they're also incorrect. Any questions on bias and variance? Because this is important. Great. Okay, so you remember how I spoke about how bias and variance are opposite problems in terms of complexity? So both lead to a failure to generalize, but what happens is that if you continue to decrease bias, there will come a point when you will start to increase variance too much. So you cannot possibly optimize for both after a certain degree. What you need to do is you need to minimize total error, find a point at which variance and bias can be both at their lowest before one starts to increase too much. All right, great. So now we're going to get into underfitting and overfitting. So underfitting and overfitting occur when an algorithm learns but fails to generalize. Underfitting is on the left, overfitting is on the right. I'm going to go a little more deeply into each of them. So high bias and low variance cause underfitting. If your model has underfit, it has underrepresented the complexity of your data set. You are not at all capturing the general pattern that you should be. And as a result, you will always have low training and low testing accuracy. However, this makes it fairly easy to spot and fairly easy to fix in comparison to overfitting. So overfitting is the opposite problem. Overfitting means you have high variance and low bias, means your results are all over the place. Overfitting is tricky because you typically have high training accuracy. When you're training, your results are great. It looks like everything is doing really well, but this is only because your model has memorized your data. So what's memorization? Memorization is when your model fits your training data perfectly and takes far too much into account the noise. So when we talk about noisy data, we're talking about data that deviates from the norm, extreme examples. So overfitting happens when your algorithm starts to encode these extreme examples and it fails to capture the general trend that you're going for. Okay, so finally, regularization. So regularization seeks to solve the problem of overfitting. Regularization addresses overfitting specifically. So a definition of regularization that I like is this one. Any modification that we make to a learning algorithm that is intended to reduce its generalization error, but not its training error. So recall earlier how we talked about overfitting, how if you continue to train a model, you will start to overtrain. It will start to memorize your data. So what regularization proposes is that it's okay if we sacrifice some training accuracy for the sake of improving our performance in terms of generalization. So I'm going to go over 4 techniques: weight decay, early stopping, dropout layer, and dataset augmentation. The first 3 are algorithmic, and the last one deals with dataset. Okay, so I'm going to start. Okay, is regularization clear? Are all the previous concepts, do we understand? Overfitting, underfitting? Yeah? Great. Good crowd. All right. So the first one that we're going to talk about is weight decay. Before I get into what it is and how it works, I want to go over with you just some of the terms on the top right. So recall that j of theta, that's your cost function, also called your loss function. What it does is measure error. So h theta x of I, that's the prediction of your model, given x of I, which is your training example, and y of I is the correct answer. So what j of theta is doing is taking both and saying, this is how far off you are, this is your error. So what we're trying to do with weight decay is address overfitting, right? And overfitting is excessive complexity. So what we're trying to do with weight decay is decrease complexity, force our model to be simpler, force it to generalize. Okay, so how this works, I'll tell you first, and then later I'll explain more in depth. So how weight decay works specifically is what you're going to do is you're going to add a regularization term to your cost function. And in front of it, you can see that's on the top there on the right. Lambda is your regularization parameter, which defines how strongly you're going to regularize. So the larger lambda, the more regularization. The smaller lambda, the less regularization. So we're going to call this updated cost function j prime. So now think of your cost function as a function of these 2 terms. Now you're no longer trying to just minimize the error. You're trying to minimize both the error and the complexity of your model at the same time. So you're saying, okay, we want you to train and learn, but at the same time, we want you to keep it as simple as possible. You're trying to generalize. So how this works is you're going to put a constraint on the actual sizes of your weights by penalizing weights that get too large. So why we want to do this is because if your weights are too large, even a small change to your input can have a really significant effect on your output. And this is indicative of variance. So if you take a look at this graph here, you can see if we have an x that's at the edge of one of these huge troughs or valleys and you move it even slightly, it'll shoot up or move down. And as you can see from the actual dots, that's not what our data actually looks like. So this clearly is a model that has overfit. You can see the high variance. So that's why we want to constrain our weights and keep them smaller to prevent this kind of variance in overfitting. Is this clear, the intuition? All right. Great. So I'm going to talk about 2 weight decay techniques called L1 and L2. I'll start with L1. L1 is often referred to as lasso, least absolute shrinkage and selection operator. You can call it whatever you want. People will understand you both ways. So the regularization term for lasso, L1 term, is the summation of the absolute values of your weights. So I'll talk later, I'll explain about how and why it does this, but what L1 does is it sparsifies your weight matrices. If you don't know what sparsify is, sparsifying, when you say that you sparsify a matrix, it means that you reduce many of your weights to 0. And for this reason, L1 is often called a built-in feature selector. So what feature selection is the process of selecting attributes from your data that are most optimal for the problem that you're trying to solve. So this is valuable because when we're training and when we're building a model, we want to eliminate this redundant data. We only want to maintain what matters. Okay. Okay, our second technique is called L2, or ridge regression. So the L2 term that we add to our cost function now is the summation of the squares of the weights. So what this does is, instead of reduce a lot of weights to 0, instead of sparsifying, what happens is that you tend to drive your weights closer to the origins. Okay. Okay. So to fully understand how weight decay works and how L1 and L2 are different, I want to go back and talk about gradients. So just a refresher on gradient descent. When you update an individual weight, what you do is you take the value of the weight and you subtract from it the learning rate times the derivative of the cost function, right? So with weight decay, with regularization, what we're doing, all that we're changing is this cost function j. We're changing it to j prime. How we're changing it is just adding a regularization term to your cost function, right? So here you can see at the bottom the updated gradients for L1 and L2. So what happens now when we take the derivative? It's no longer a derivative just of our cost function. It's of our updated cost function, which is in addition this new term. So what happens is that the derivative of L1 becomes a constant k, which is independent of the value of the weight that we're updating. It's related to the summation of all their absolute values. And the derivative of L2 turns out to be 2 times that weight. So for those of you who remember calculus, the derivative of x squared is 2x. And a lot of times what people will do is they'll scale it down to get rid of that coefficient by dividing by 2, which you can do, you don't have to. It won't affect the effectiveness of weight decay. Okay, so what this actually means, the difference then between L1 and L2 is that L1 will reduce all of its weights evenly because it's subtracting this one constant from all of the weights. What L2 does, it penalizes larger weights because of that squared, right? So it'll penalize larger weights more than it'll penalize smaller ones. So this is why L1 causes sparsity and L2 just restricts and pushes down all your weights, is because when you're reducing your weights by this constant, the ones that are small are going to get zeroed out, and the ones that are large are just going to be reduced by that constant. But you can think of L2 instead of reducing a weight by a percentage instead, and that's how they're different. That's how they differ. Also, L2 is computationally easier to implement than L1, so it's more commonly used than L1. Any questions about L1, L2, weight decay, why they're different? Yes.
Is L1 or L2 better for certain things, or?
L1, in its value that it has as a feature selector, that's why some people prefer L1, but most people prefer L2 because it's easier to implement. Yeah. Any other questions? Is this clear? Okay. Okay, so more on this regularization parameter. So again, it regulates how strongly we're going to regularize our model. So if it's larger, the more regularization it's going to apply. If it's smaller, the less. However, it is just another hyperparameter, like learning rate, for example. So you're not going to be able to guess the correct one at first. You're also going to have to pick a couple of different models and test for it. Yeah, there's no golden number. I'm sorry. It's just one of the things that you're going to have to trial and error. But it's important to remember that if you make it too large, you're going to cause high bias, and you're going to penalize the parameters too much, and you're going to end up underfitting. But if you make it too small, you're going to cause high variance, and you're not going to penalize the parameters enough, and you're going to cause overfitting anyways. So just something to be aware of. If you actually do this, you'll know, but just something to keep in mind. Okay, our next technique is called early stopping. So early stopping says let's prevent overfitting before it even happens. Remember earlier how I talked about how over time you can tend to, if you overtrain, you'll overfit. So what early stopping says is, okay, plot your validation error alongside your training error, and when validation error increases too much, then just stop training because any more and you're going to overfit. So just note, we train in epochs. So one epoch is one iteration over your entire data set. And then after that, you'll perform on your validation set and save the parameters. And a validation, that's what I mean when I say plot validation error alongside your training error. Okay, but it's not this neat actually in practice, unfortunately. So you're not going to have this one really smooth minimum here. Typically, you're going to have a bunch of local minima. So how do you actually know when to stop? If you stop the very second validation error starts to increase, you might not reach your optimum point of training. So you use stopping criteria, which you determined beforehand. So what you could say is, all right, if validation error increases this much over one epoch, then I'll stop. Or you could say, if validation error increases this much over several epochs, then I'll stop. These are just a couple of examples. There are more, which I've included at the end, which you can take a look at if you're interested. All right, does everyone understand early stopping and the intuition behind it? Cool. I appreciate the ones that nod back at me. I appreciate the feedback. All right. So another popular regularization technique is called dropout. It can seem kind of counterintuitive because what you're doing is you're literally going into your network and randomly killing neurons. Okay, so the intuition behind this is that you're trying to force your network to encode the same amount of information into less nodes. But more importantly, you're trying to address the issue of co-adaptation. So typically what happens when you're training your network, it goes right alongside with overfitting, is that nodes tend to change in response to the changes of other nodes. They try to account for their mistakes too, and they become, in a weird way, like codependent, interrelated. And this is not what we want, because we want our individual nodes to train for more general patterns. We don't want them to depend on the existence and context of other nodes around them. So what dropout does is by randomly killing nodes, from the viewpoint of one single individual node, you can't trust your neighbors any longer because they might not exist. So it's up to you individually to take what you know and try to find broader patterns, regardless of what your other nodes are doing. So one implementation of dropout is called inverted dropout. So I'm going to illustrate this on a single layer. So what you do is you set a probability P of dropping a given node in that layer. So let's say 40%, 0.4. So what you then do for this layer is create a vector D of the same size, same number of elements, and randomly set the elements in D to either 1 or 0 in accordance with your probability P. So if you have 5 elements in D and your probability is 40%, 40% or 2 of your nodes are going to be 0 and 3 of them are going to be 1. So what you then do is you multiply the activations of L by D, effectively reducing P percentage of your node values to 0. All right, is that clear? Yeah.
Would you add back nodes after you get rid of them? After you relearn the dropout?
Kind of, yes. As you pass training examples past them, as you pass training examples through them again, you're not like physically removing them out, you're just making them 0. As you pass more examples through, they will have value added back into them.
Okay.
Yeah. Yeah.
Well, like every top, there's like some random note that effectively just says, okay, I'm not doing work right now.
Yeah. Yeah. It's like that. Do you understand why that works, the intuition behind it? You can say no. Kind of? I can go over it again. Yeah.
So what is the computational advantage of this drop-down method compared to literally just training it until the weight goes to zero?
Computationally, if you want a numerical comparison, I don't know, but it is proved to be very effective. That I can tell you. I've included the link to the paper at the end, so you can take a look at it for yourself if you want. All right. Should I? Yeah.
Why is 1 minus 2.8?
Oh, 0.8. I'm gonna explain that. That has to do with step 4.
Yeah.
All right. So, yeah.
So how do you propagate if your connection is changing every single iteration?
Your connection isn't changing. You're not physically removing those nodes. You're just changing their values. Their values are 0. They still exist there, but you're removing their influence on their neighbor nodes.
What if the gradient of that node suddenly becomes 0? What if you drop out the node and then the gradient of operation is like 0? I think I'm trying to aware just for that iteration because you're changing the node rate up multiple times. Just for that iteration, you just don't that complicated. Oh, okay. Because like you're not doing that. You didn't store that. Okay.
Okay. Any more questions? Okay. So having now effectively removed p percentage of nodes from your layer, what you will now do is you want to scale up the value of these existing nodes, but of these remaining nodes, by your quote-unquote keep probability, which is 1 minus your drop probability, which in this case would be 0.8, to maintain the expected output value. This is because you only implement dropout during training, and you don't implement dropout during testing. So you want to scale up the values of your weights that you've dropped during training so that the average output during training will match your output during testing. So that makes sense? Because otherwise it would be like you would be having different, you would have different networks. So you have to maintain this kind of expected output value for each. Yes? Oh my god, you're so right. Used to be. Oh, I see. Yeah, it's supposed to be 0.6. I changed it. Yeah. Good catch. You're going to be good at this. All right, any other questions on dropout? Is the intuition clear behind dropout? Yeah, and the other guy who asked the question. Is the intuition behind dropout clear? Like the point of removing nodes completely so that they don't become dependent on each other.
Like you kind of like remove their influence altogether, so therefore their input does not matter to this epoch for now. Like that's sort of this epoch does not matter.
Yeah, kind of. It's more for the sake of the individual nodes. You don't want them to only be useful in clumps. You want them to each individually be valuable. Oh, cool. So the last technique that I'm going to talk about is dataset augmentation. So the most straightforward way to improve any machine learning algorithm is to just give it more data. But you don't always have a huge wealth of data available to you, and especially not for the specific problem, not always for the specific problem that you're trying to solve. So what you can do if you need more data is to create new fake data by making small edits to your existing data set. So what you want to do is change it just enough so that it could be considered new data, but not so much that it changes the classification. So for example, if you're classifying numbers, don't flip a 9 and make it a 6. That's not smart. But what you can do is like rotate or scale images. You can change the lighting, you can blur or crop them. So this can be useful in a pinch to create lots of new data, but it's never as effective as using brand new data. All right, any questions? Dataset augmentation? Cool. Okay, so to summarize, weight decay is the practice of penalizing weights that get too large by adding a regularization term. To reduce complexity, early stopping is tracking your training and validation error to stop overfitting before it even occurs. Dropout is randomly killing neurons in your neural network to prevent co-adaptation. And dataset augmentation is the practice of creating new data from pre-existing data. Any questions on any of these? Because this is the end. This is your last chance. Yeah?
Can you go over co-adaptation?
Co-adaptation? Sure. So, co-adaptation is something that we see during training that's related to overfitting. Basically, when you calculate your loss at the end of forward propagation, it's loss relative to all of your weights, right? So when you back propagate these derivatives, these values are not, when they reach an individual node, an individual weight, that value has been influenced by all of the other weights that have come before it. So individual nodes have a tendency to change in relation to other nodes. So what can happen is that individual nodes can become too dependent on other nodes for context, and they can become maybe only valuable when these other nodes are also activated or in use, right? So this is obviously not ideal. We want all of our nodes to function as well as they can individually. We don't want them to only be effective in groups or in clumps. We want each one to encode valuable data. We want each one to look for the more general patterns in our data set. That's why. Yeah.
Is there a limitation on how many drops on nodes you can have compared to data set? Considering that if you drop out too many nodes, then you basically drop under 50.
I would say yes. I don't know what that is, but I've known dropout to be implemented with up to like 50% of nodes dropped, and that has still been effective. So that definitely exists, and I'd be interested to know what that is. But yeah.
Theoretically, right? But like, of course, we draw out 97. I think right now is 50.
Any other questions? Yeah.
So for weight decay, how do you know you're reducing parameters that like are overfitting rather than just parameters that are important?
Okay, so individual parameters don't overfit. Overfit is something that occurs across all parameters. I see what you mean though, because when you high variance, it's like you're taking into account those like extreme examples. The point is not to say ignore these specific examples. The point is to say look at the general trend. So the point is, so you're saying like don't take each individual example into account too much. Try to generalize. Yeah. Any other questions? All right, that's all. Thanks, guys. And some more resources if you want them. But everything's going to be posted anyways. Cool. Thanks for coming.